On October 11th, 2025, as NASA issued a 3-paragraph statement classifying the telemetry blackout of the 3I Atlas Orbital Telescope as an unprecedented event, the European Space Agency postponed the publication of its full logs for 6 weeks, citing a review of cybersecurity protocols. 12 hours and 17 minutes of absolute silence. A near-Earth object surveillance satellite, specifically designed to operate autonomously for decades, simply ceased all communication. When transmissions finally resumed, something vital was missing, not just time, data. 1,400 gigabytes had utterly evaporated from its onboard record. The pressing question isn't merely what transpired up there, it's what they are still not showing us. In 23 years of autonomous orbital missions, an observatory of this magnitude has never gone silent for so long without immediate explanation. The 3I Atlas is not an experimental CubeSat. It is a 4-ton platform the size of a large SUV, equipped with 3 mid-infrared spectrometers and a redundant communication system designed to survive the simultaneous failure of 2 transponders. Positioned in a sun-synchronous orbit at 680 kilometers altitude, it crosses the same points of the globe at the same solar time every day, capturing asteroids, comets, and space debris with Swiss clock precision. Its job is to warn us when something dangerous approaches. But on October 11th, who was watching the Watchman? In 12 hours and 17 minutes, it completed nearly 8 full orbits, covering a vast swath from the Arctic all the way to the Antarctic, passing over all continents. During this period, its sophisticated sensors should have captured 3 terabytes of crucial raw data: thermal imaging of asteroids, subtle albedo variations, and distinct spectral signatures of volatile compounds. The onboard recording system has a substantial capacity of 4.8 terabytes. There was absolutely no risk of data overflow. Yet, when the telemetry dump finally occurred a full 41 minutes late, only 880 gigabytes reached the ground stations. This represents 62% of the expected data, completely missing. The most critical gap? 43 minutes, precisely centered over its passage through the South Atlantic anomaly, that notorious region over Brazil and the Atlantic where Earth's magnetic field dips closest to the surface, and charged particles bombard satellites with notably greater intensity. In that specific area, sensor degradation is certainly expected, but never, under any circumstances, total memory loss. The Mauna Kea Observatory in Hawaii maintains an optical satellite tracking program for collision avoidance. On the night of October 10th to 11, its automated telescopes registered something highly unusual: a luminous transient of apparent magnitude +4. 2, lasting 11 seconds, was perfectly aligned with the predicted orbital position of the 3I Atlas. Magnitude +4.2 is the brightness of Saturn when seen with the naked eye on a clear night. An aluminum satellite with solar panels, even at an angle favorable to the sun, rarely exceeds magnitude +2. A second confirmation came from the Las Campanas Observatory in Chile. 17 minutes later, another flash, magnitude +4.1, the same signature. The third record was from the Haleakala Observatory, also in Hawaii, magnitude +3.9. 3 independent stations, separated by thousands of kilometers, all capturing the same phenomenon. How can we explain a satellite with a non-reflective surface shining like a gas giant? 3 independent stations, separated by thousands of kilometers, detecting the same phenomenon. How to explain a non-reflective surface satellite shining like a gas giant? During the final minutes of the blackout, civilian radio telescopes of the X-band monitoring network, operated by the Inter-American Radio Astronomy Consortium, detected a pulsed signal coming from the orbital region of 3I Atlas. Frequency between 8 and 12 gigahertz, X-band, used for high-rate space communications. The signal had an exact periodicity of 1.37 seconds. The satellite's known transponders operate in S-band between 2 and 4 gigahertz and transmit in data bursts, not regular pulses. The difference is crucial. Bursts are packets of information sent when there's something to communicate. Regular pulses are beacons, signs of presence, as if something were saying, "I'm here." The signal lasted 4 minutes and 22 seconds, then silence. 3 hours later, 3I Atlas resumed normal transmissions, as if nothing had happened. To achieve magnitude +4, 3I Atlas would need to reflect at least 40 times more light than its geometry allows. Even considering a solar panel perfectly aligned with the sun and the observer, something called specular reflection, the theoretical maximum would be magnitude +1.8. The calculations are straightforward. The satellite's reflective area is approximately 18 square meters. The observed luminous intensity would require an area of at least 720 square meters, equivalent to 3 tennis courts, or its own light source. But observation satellites don't carry spotlights. Their power systems barely cope with sensors and heaters that prevent instruments from freezing in a vacuum. The only conventional explanation would be a multiple reflection event, where sunlight bounces between polished surfaces at specific angles. But this would require geometric alignment with less than 1 degree of precision, maintained for 11 seconds, while the satellite moves at 27,000 kilometers per hour. Probability? Less than 1 in 10,000. The 43-minute gap in the recovered data is not random. It is centered, with a margin of error of 90 seconds, on 3I Atlas's passage through the South Atlantic anomaly. This region, extending from southern Brazil to the mid-Atlantic, is known to temporarily degrade electronic sensors. Charged particles from the solar wind, trapped by Earth's magnetic field, dive deeper there, hitting low Earth orbit satellites with high doses of radiation. Memory bits can flip. Sensors can generate spurious readings. But space data recording systems are designed with triple redundancy precisely for this. Each byte is written to 3 separate chips, and an error correction algorithm reconstructs the information even if 2 of them fail. Losing 43 continuous minutes would require simultaneous failure of at least 6 independent electronic components. The probability of this happening by chance, according to space system reliability models, is less than 0.3%, or it was no accident. At least 6 independent electronic components. The probability of this happening by chance, according to space system reliability models, is less than 0.3%, or it wasn't by chance. Leticia Mora, an RF systems engineer at the National Institute for Space Research, states that a pulsed signal with such stable periodicity, 1.37 seconds with a variation of less than 2 milliseconds, is not generated by conventional communication systems. It's more akin to what we would use for network synchronization or as an emergency beacon. But the 3I Atlas doesn't have X-band transceivers on board, at least not in the public blueprints. The consortium operating the satellite, led by NASA and ESA, never listed X-band equipment in any technical documentation. If the signal came from the satellite, there's undeclared hardware. If it didn't, something else was transmitting from the same orbital position during the blackout. Space debris does not emit radio signals, at least it shouldn't. On October 11th, 2025, its center was approximately 28 degrees west longitude and 23 degrees south latitude, over the ocean between Rio de Janeiro and the coast of Namibia. The 3I Atlas's sun-synchronous orbit crosses this region twice a day, once on the ascending pass and once on the descending pass, but the data gap only occurred during one of the passes, the descending one between 1437 and 1520 UTC. On the subsequent ascending pass, 7 hours later, the systems recorded normally. Why would the anomaly affect the satellite on one transit but not the other? Solar wind conditions were stable that day. The KP index, which measures geomagnetic disturbances, was at 2, considered calm. There were no solar storms, no particle bursts. The radiation should have been identical on both passes. When a satellite loses power or suffers a critical software failure, it enters safe mode, a minimal state where only essential systems remain active while the onboard computer restarts. This process takes between 8 and 45 minutes, depending on the architecture. The 3I Atlas took 12 hours and 17 minutes to resume transmissions. During this time, it continued orbiting, maintaining a stable attitude, pointing its solar panels towards the sun. We know this because optical tracking stations continued to observe the satellite at expected times, with the typical brightness of the panels, except for 3 anomalous flashes. Maintaining attitude requires that the momentum wheels, small wheels that spin at 6,000 revolutions per minute to control orientation, remain active. They consume power. If there was a power failure sufficient to knock out communications for 12 hours, the momentum wheels would have stopped. The satellite would have entered tumbling uncontrolled rotation. Ground observers would have seen erratic variations in brightness. They didn't. The 3I Atlas maintained perfect attitude control during the silence. How? Ground observers would have seen erratic brightness variations. They didn't. The 3I Atlas maintained perfect attitude control during the silence. How? Scientific class satellites like 3I Atlas carry 2 onboard computers, a primary and a backup, which can take control in seconds if the main one fails. They also have 2 independent communication transponders, powered by separate electrical buses. To completely lose telemetry, you need to knock out both computers and both transponders simultaneously. Radiation events don't do this. Micrometeorite impacts can puncture one component, but hitting 4 physically isolated systems in different positions on the structure would require catastrophic fragmentation, and in that case, the satellite would not resume operation. The only common failure that could silence everything simultaneously would be a total loss of power, but the 3I Atlas solar panels generate 2.8 kilowatts under normal conditions. Even in Earth's shadow, when the satellite passes through orbital night, lithium-ion batteries keep all systems running for up to 50 minutes. The blackout lasted 12 hours. If the batteries were depleted, the panels should have recharged during each pass through the daylight side, approximately 60 minutes of sunlight every 90 minutes of orbit. In 12 hours, the satellite had at least 8 recharge cycles. Why did it take so long to wake up? The 5th anomaly is the selective data loss. it's not just a 43-minute gap. Preliminary analysis of the 880 gigabytes recovered shows that the missing data corresponds exactly to imaging of a specific strip of the sky. Coordinates between right ascension 1430 and 15820. Declination between 15 and 1220 degrees. This region of the sky hosts the constellation Libra, parts of Virgo and Scorpius. Nothing particularly interesting there except for one detail. On October 11th, asteroid 99942 Apophis was transiting at plus 118 degrees declination, well within the lost strip. Apophis is famous. On April 13th, 2029, it will pass just 1,600 kilometers from Earth, closer than GPS satellites, one of the closest recorded flybys for a 370-meter diameter asteroid. The 3I Atlas had a secondary mission to map Apophis in multiple wavelengths during 2025, building a detailed thermal and compositional model before the 2029 encounter. The October imaging window was critical, with Apophis visible at a favorable angle and still at a measurable distance for instrument calibration. Now, that window is gone. Coincidence? There are about 34,000 tracked objects in Earth orbit larger than 10 centimeters in diameter. Below that, estimates speak of 130 million fragments between 1 and 10 millimeters. A 3-millimeter piece of debris, traveling at 10 kilometers per second in a counterorbit, carries kinetic energy equivalent to a rifle bullet. This would be enough to puncture panels, damage exposed electronics, but the 3I Atlas remains operational. Its post-blackout images show unaltered spectral resolution. If there was an impact, it did not hit any critical component. Furthermore, impacts generate secondary debris, ejected fragments that create detectable signatures for space surveillance radars. The U.S. Space Command's radar network, which monitors objects above 5 centimeters, reported no new fragment cloud in the 3I Atlas's orbit. This hypothesis does not hold up. Space Command's radar network, which monitors objects larger than 5 centimeters, reported no new debris cloud in 3I Atlas's orbit. This hypothesis does not hold up. Code bugs can crash computers, and in a space environment, a crash might take time for thermal cycles or automatic resets to clear memory. But 3I Atlas runs 2 different operating systems, developed by separate teams, precisely to prevent a common bug from bringing them down simultaneously. Furthermore, telemetry logs from the days prior to the blackout showed no anomalies, no accumulated errors, no signs of performance degradation. The satellite was operating within nominal parameters up to the exact minute it stopped transmitting. Software failures are rarely so abrupt. They usually leave traces, error messages, restart attempts, partial communications. 3I Atlas simply disappeared for 12 hours, then returned with no diagnostic messages, no exception reports, nothing, as if it had been deliberately shut down and then restarted. The third explanation, electromagnetic interference. Electromagnetic pulses, natural or artificial, can induce spurious currents in electronic circuits, causing resets or permanent damage. Intense solar storms have brought down satellites before. But on October 11th, the Sun was in a period of low to moderate activity. There were no M-class or X-class flares in the 48 hours prior to the event. Terrestrial magnetometers, which measure the intensity of the geomagnetic field, registered no significant perturbation. If there was an electromagnetic pulse, it was localized, hitting only 3I Atlas without affecting the other 47 satellites orbiting between 650 and 700 kilometers at that time. This is not physically impossible, but it would require a directional source, something like a high-power microwave beam. And this leads us to uncomfortable territory. All have developed anti-satellite weapons, ranging from kinetic missiles to high-energy lasers and electronic jamming systems. In theory, an electronic warfare system could bombard a satellite with intense radio signals, overloading receivers, forcing resets, or even burning out components. But 3I Atlas is a civilian scientific satellite, operated by an international consortium that includes agencies from 14 countries. Attacking it would be a political act of enormous proportions, without clear strategic benefit. It carries no military sensors, it doesn't spy on anyone, it merely observes asteroids. Why would anyone silence it? Unless it saw something it shouldn't have seen, or unless someone needed to ensure it didn't see Apophis at that specific moment. Unless it saw something it shouldn't have, or unless someone needed to ensure it didn't see Apophis at that specific moment. Not an asteroid. Another functional uncatalogued object operating at the same altitude. There are classified military satellites whose orbits are not published. There are remnants of old missions, upper stages of rockets that failed to deorbit, abandoned capsules from 1970s Soviet programs. If 3I Atlas got too close to one of these objects, security protocols could have automatically shut down its transmitters to prevent collision or data contamination. But that wouldn't explain the flashes of light, nor the X-band signal, nor the selective loss of data concerning Apophis. Each explanation covers one anomaly, but none covers all of them. It's as if we're looking at a puzzle where the pieces don't belong to the same set. Some have suggested that 3I Atlas might have been the target of an unannounced space weapon test. Others have raised the possibility that the satellite captured something governments are not yet ready to discuss, perhaps an object on a collision course with Earth that would require massive civil preparation. There are even those who speculate about natural phenomena not yet understood, plasma eruptions from the ionosphere, or interactions between Earth's magnetic field and high-energy particles of unknown origin. None of this can be categorically dismissed, but neither do any of these hypotheses have sufficient data support to be asserted. What we have are questions, and institutional silence. NASA issued its statement 3 hours after 3I Atlas resumed transmissions. 3 paragraphs, no details about the cause, only confirmation of a temporary telemetry interruption due to a non-nominal event under investigation. The European Space Agency, responsible for the ground segment and initial data processing, stated that complete logs would be available after review of cybersecurity protocols. That was on October 12th. Today, 6 weeks later, the logs have still not been published. Cybersecurity review usually takes between 72 hours and 2 weeks. 6 weeks suggests something beyond standard procedure. It suggests filtering, redaction, or awaiting political authorization. The consortium funding 3I Atlas includes contributions from 14 countries. Decisions on data release and multilateral missions can get bogged down in diplomatic bureaucracy, especially if there's suspicion that a consortium member was involved in the incident. Decisions regarding data release and multilateral missions can get bogged down in diplomatic bureaucracy, especially if there's suspicion that a consortium member was involved in the incident. Meanwhile, the scientific community that relied on 3I Atlas data for publications entered a forced standby mode. At least 4 articles on the chemical composition of comets, which would have used October's data, had their submissions postponed. A group from the University of Arizona studying seasonal variations in inner belt asteroids lost the observation window for 3 objects that will only return to favorable positions in 2027. And the International Consortium planning planetary defense missions against Apophis needs the calibration data that 3I Atlas should have collected precisely during the lost window. Without this data, trajectory models for 2029 carry an additional uncertainty of 2 kilometers in the closest approach distance. It might not seem like much, but during a flyby at 31,600 kilometers, where Earth's gravity will complexly deform Apophis's orbit, 2 kilometers of uncertainty could mean the difference between a safe transit and the need to evacuate communication satellites. If 3I Atlas sensors were damaged or uncalibrated during the October blackout, and if the ground team cannot correct them by then, we lose the last chance to refine models before the 2029 flyby. Apophis does not pose an impact risk in 2029, this is well established. However, the encounter is a unique scientific opportunity. An asteroid of this size passing so close allows for measurements of internal composition, gravitational structure, and Earth's tidal effects on a solid body. We've never had this chance before. If 3I Atlas is not operational, alternatives are limited. Ground-based telescopes can make visible observations, but mid-infrared, essential for thermal maps and detecting hydrated minerals, is blocked by the atmosphere. Other space telescopes, like James Webb, have full schedules and cannot be easily redirected. Losing 3I Atlas means losing the only instrument dedicated to this task. If 12 hours were enough to compromise a critical satellite, how much time would be needed to silence an entire space surveillance network? There are about 20 orbital observatories dedicated to tracking near-Earth objects, distributed in low, medium, and geostationary orbits. Most share similar communication architectures, S-band transponders, gyroscopic attitude control systems, and onboard computers from European and American manufacturers. If there's a common vulnerability, be it hardware, software, or protocol, an actor with sufficient resources could exploit it sequentially. Imagine 3 or 4 satellites going silent over a few months. The scientific community would be blinded precisely when we need more eyes in the sky. The number of potentially hazardous asteroids discovered per year grew from 12 in 1998 to over 300 today. This doesn't mean there are more asteroids. It means we are finding those that have always been there. If we stop looking, we return to ignorance. This doesn't mean there are more asteroids. It means we are finding the ones that have always been there. If we stop looking, we revert to ignorance. The International Astronomical Union maintains a small body data coordination center, which aggregates observations from multiple sources. If one telescope fails, others can partially cover the gap. But mid-infrared imaging capability is scarce. Only 5 orbital instruments operate in this range, and 3I Atlas was the most sensitive. Replacing a satellite of this magnitude would take between 5 and 8 years, from design to launch, at an estimated cost of $850 million. No consortium approved funding for a backup. The strategy has always been to keep 3I Atlas operational for as long as possible, extending its original 10-year lifespan through careful propellant-saving maneuvers and partial sensor hibernation cycles. It completed 8 years in orbit. We expected at least 7 more. Now, we don't know if it will last until March. A small service satellite, equipped with high-resolution cameras and a robotic arm, could be launched to rendezvous with 3I Atlas, inspect its external structure, look for signs of impact, damaged antennas, misaligned panels. Orbital servicing missions have been done before, most notably for repairs to the Hubble Space Telescope. But these operations cost hundreds of millions and require approval from multiple agencies. The political cost of admitting we need to inspect the satellite because we don't know what happened might be higher than the financial cost. Furthermore, approaching an operational satellite in orbit is technically risky. If the maneuver fails, you create debris. If successful, but the satellite interprets the approach as a threat, security protocols could permanently shut it down. We are at an impasse. We need answers, but actively seeking them might destroy the only instrument we want to save. We built 3I Atlas to warn us of threats from space. But perhaps the threat isn't from runaway asteroids. Perhaps it comes from our own inability to protect the infrastructure that protects us. Low Earth orbit is becoming increasingly congested. Mega constellations of internet satellites add thousands of new objects each year. Debris from anti-satellite weapon tests circulates in lethal clouds. Accidental collisions become more probable with each launch. And now, for the first time, we've seen a large scientific satellite inexplicably go silent for half a day, brighten like a star, and lose data on an asteroid that will cross our orbit in less than 4 years. If this is the new normal, we need to rethink the entire architecture of space surveillance. Redundancy is no longer enough. We need diversity. Terrestrial instruments, orbital positioned at Lagrange points, perhaps even probes accompanying the most dangerous objects in their own orbits. But this requires international coordination on an unprecedented scale, and political will that, frankly, I don't see. Perhaps the telemetry logs, when finally released, will show a trivial sequence of cascading failures, something engineers could correct with a software update or a thermal control parameter adjustment. Perhaps the one. 4 terabytes lost are irrecoverable, but the sensors prove to be perfectly calibrated and the mission continues as planned. Or perhaps we'll discover that something tested our limits, pushed our systems to the breaking point, then retreated before causing irreversible damage. A warning, not an attack. If so, the message was received. We are vulnerable, and we have 4 years to prepare, not just for Apophis, but for whatever else might be out there, silently orbiting, waiting. And if you have data, analyses, or work at a space agency and can speak, the comments are open. Transparency is not optional in science. It is the only way. But every now and then, something out there seems to pause. It seems to look back. And in the silence that follows, we carry the only certainty we have. 12 hours can change everything, or nothing.